guys, Miss Brumwell here. This video is for section 1.2. We're going to start looking at other ways to find limits than using a table and a graph. So one of the ways we can evaluate limits is by knowing a couple of basic ones. So anytime I'm finding the limit of a constant, remember a constant's a number without a variable, it doesn't matter what x is approaching, it's going to be that constant. Also, if x is approaching a number and we want to find that limit of x, then x is just, that limit is going to be equal to whatever number it's approaching. The reason for this one is a horizontal line, so it doesn't matter what x value it is, it's the same y value or limit that it's going to be approaching. This one, the function y equals x is just that 45-degree angle line with a slope of 1. So x and y are always equivalent on that line, no matter where the point is and what x value we're approaching. So that's why those are true. So for these first two examples, the limit as x approaches 5 of 2 is equal to 2. Okay, so that's using that first basic limit. It does not matter what x is approaching. If it's a constant, it's equal to that constant. This one wants us to find what is the limit as x approaches the square root of 3 of x. So essentially, it's saying that as x approaches root 3, what's y approaching? So remember, for this function, y and x are always equal. So whatever value I'm approaching is what my limit is. Okay? All right. Here's some properties of limits. These are in your book. I just summarized them in one place. Basically, this is saying if we have two different functions and we add or subtract them, that's the same as adding and subtracting the limits. So that's great. When we multiply them, same is true. If I multiply a limit by a constant, so a number, that's what k is, it's the same as the constant times the limit of that function. We can do a similar property with powers as we can with roots. So if I'm finding the limit of a function raised to a power, that's the same as me finding the limit of the function first and then raising it to that same power. And very similar with the roots there. We can also have rational exponents, which remember is another form of a root depending on what the fraction is, but n is the root, m is the exponent. Limit of a quotient. So when I divide two functions, really I can again find the limit of each and then divide them, but this is important. The limit of my denominator cannot be 0, right? Because I cannot divide by 0. And we're going to talk about that a little bit later on. If I'm finding the limit of a polynomial function, all I have to do is substitute in c. And same is true for a rational function. So we're going to do a couple examples here, kind of using those properties. So this is going to be huge, you guys. I'm going to kind of show you some longhand in the notes a little bit, but as you get more comfortable with these, basically anytime we're evaluating limits is we're going to substitute in the x value we're approaching. We are going to run into some issues later on with that, and we'll teach you guys some techniques for how to deal with that. Right away though, these basic ones, substitution is going to be our main strategy. Okay. And then limit properties, these properties are also true for one-sided limits. Okay, so let's look at this example. Again, I'm going to kind of do longhand on the first couple and then we'll just jump into substitution. But here, I want to find the limit as x approaches -3 of this function, x plus 4. Well, this is the same as the limit as x approaches -3 of x plus the limit as x approaches -3 of 4. Well, these are those two basic functions that we just saw up above, right? This limit is equal to -3, right? When I'm finding the limit of x, I just substitute in that c value. And then the limit of a constant, it doesn't matter what x is approaching, is going to equal that constant. So this is where I could kind of break it into two limits and add them together. So -3 plus 4 is 1. So this limit equals 1. Okay. This one, very, very similar, but it's subtraction. So the limit as x approaches 4 of 6 minus the limit as x approaches 4 of x. Okay, so then we have a constant again, so 6 minus, I'm just, anytime I'm evaluating a limit of x, I just substitute my c value, so we've got 6 minus 4, which equals 2. All right. Okay, Some more examples here, you guys. Okay, so this one involves a product and a sum. So the same is true here. I could like evaluate each piece and I can multiply those together. So this is actually at this point, you guys, I am gonna just substitute in whatever I'm approaching for x in for all the x's. So this is the strategy you always actually want to start with when evaluating a limit without a graph or a table, is we're just always going to try substitution. I'm going to substitute in my c value for all my x's. Because all those algebraic properties work, that's why I can do this. So I'm going to do 2 times 1 and then times 1 plus 4. Okay, so we've got 2 times 5, which equals 10. So our limit of that function as x approaches 1 is 10. Okay, now the powers, same thing. So I'm going to write this out longhand. Again, we're essentially using substitution, but I just want to remind you this is the same as this whole limit, the limit as x approaches 1 of 2x minus 3. So I could evaluate this limit first and then raise it to the third power. So essentially same thing again. I'm going to substitute in my x. So we have we're substituting in our c value 1, so we've got 2 times 1 minus 3, and then raising that to the third. So 2 times 1 is 2, minus 3 is negative 1 to the third is negative 1. Okay, the root is the same idea as we did here. This is the same as the cube root of the entire limit. So the limit as x approaches 4 of x squared plus 11. So I can evaluate this first and then take the cube root. Again, I'm substituting in my c value of 4. So I'm finding the cube root of 4 squared plus 11, which is the cube root 27, which is 3. Okay, so reminder here, this is again a power or a rational exponent. 2 is the root, 3 is the power. So this one is the same as, again, I'm going to substitute in 8 here. So I've got 8 plus 1 to the 3 halves. That's the same as 9 to the 3 halves, which is the same as the square root of 9 cubed. So square root of 9 is 3, 3 cubed is 27. So the denominator is the root, the numerator is the exponent. Okay, this is a polynomial, right? A polynomial is, I have integer exponents, right? Sorry, I should say positive exponents. And I can evaluate the same way I just was. We're substituting our c value in for x. So I've got 7 times negative 1 to the 5th plus 4 times negative 1 to the 3rd minus 2 times negative 1 squared. Really just important that you follow order of operations here. Do all those exponents first before multiplying. And you should get here negative 1 times 7 is negative 7. Negative 1 times 4 is negative 4. This becomes positive 1, but times negative 2 is still negative 2. So when I subtract all those values, I should get negative 13. Okay, rational function, again, we can start with substitution. I just have to make sure my denominator doesn't equal 0 when I substitute this value in. So let's go ahead and do that. So I've got 2 times negative 2 plus 4 over 3 times negative 2 squared minus 1. This is not going to give me 0, so we're okay, we can proceed. All right, so I've got what? Negative 4 plus 4 is 0. And here I have 12 minus 1 is 11. 0 divided by anything is 0. Okay, these next two are what we call piecewise functions. Now this one doesn't look like a piecewise function, it looks like absolute value, but I'm actually gonna redefine this. Anytime we have absolute value, guys, I have this expression as a positive or a negative. So I'm gonna say that f of x equaling this is equivalent to this function. F of x equals, so piecewise function has different range values for x that are defined a certain way. So for the first one, it's I'm going to get rid of the absolute value because absolute value, remember, what's inside could be negative or positive. So the first one is make what's inside negative. So I'm just going to put that -1 out front. Okay, so it's defined that way if our x's are less than 1. And actually, notice this. These are the same thing, right? X minus 1 divided by x minus 1 is 1. So this whole thing's just going to equal -1. And that happens when x is less than 1. Now, you might say, what happens when x is 1? Well, I get division by 0. So that actually is not defined for this function. So then it's the positive version, same thing. Well, that's just that thing divided by itself, which is +1, and that happens if x is greater than 1. Okay, so here's my two pieces. So this is just good to know that this is another way to define absolute values, a negative of that expression and a positive of that expression. These ones simplify nicely to just -1 and 1, okay? So in this case, if I have a piecewise function, I want to know the limit as x approaches 1 of this function. When I have pieces that are given ranges above and below that c value that I'm approaching, I need to find the one-sided limits. So I'm going to find the left-hand limit. So we have the limit as x approaches 1 from the left. Okay, well, and I'm just going to write of f of x so I don't have to write the whole thing out. Okay, so of this function, well, here's my situation. If x is less than 1, right, that's numbers from the left of 1, then it equals -1, right? If I were to plug in any number less than 1, getting close to 1, I'm going to get -1. Now, if I approach it from the right of this function, so numbers greater than x, I'm going to get it to equal 1. Those are the two different values that this function equals. So remember, if the one-sided limits do not equal each other, the limit does not exist. Okay? And we don't write equals does not exist, we just write d and e. Okay? All right, here's another piecewise function. This one wants us to look at 1. So I can use substitution here still. But again, if it's a piecewise, I'm going to use the left and right-handed limits. So I'm going to look at the limit as x approaches 1 from the left of f of x. So I don't have to write the whole thing. So from the left is less than 1, so I'm going to use this guy. So we have the limit as x approaches 1 from the left of x minus 1. This part is important because I notice I didn't write all of f of x again. I showed which piece I'm using that fits this one-sided limit. So if I'm doing this again, make sure you rewrite limit with x approaching your value. If you leave this out, that is a notation error that you would be marked off for on an AP exam. So do not get rid of this part of your expression until you substitute in your number. So I'm now going to substitute in my number 1, So I'm plugging in 1. 1 minus 1 is 0. Okay, so there's my left-hand limit. We got to check the right-hand limit as well. So if x approaches 1 from the right side, so that's going to be x is larger than 1, I'm going to use this piece. So the limit as x approaches 1 from the right of f of x. So I'm going to again show what piece that is exactly. So that's just this part. Okay, and now I'm going to plug in 1 for x. And I also get 0. So the left hand and the right hand limits both equal the same number. So that is our limit. So we're going to say the limit as x approaches 1 of f of x equals 0. So if they both equal the same thing, I can say the overall limit is 1. Even though 0 is not defined in this function. Oh, actually, no, it's fine. Okay, sorry. Thinking of a different problem. Okay, so our limit as x approaches 1 of this function is 0 because both our right hand and left hand limits are the same.